So hey everybody who's out there, these are video reviews for Data A test, exponentials, and logs. We just did this one example problem. If you want to take a screenshot of that, you can see the algebra involved. I'll probably do another one. We also just graphed it too to show that we get the exact same solution. Okay? So we're going to start off with some vocabulary. So what are some of the things that you need to know? And I got a lot of it on here. So some of it is going to be a little bit of review things from the prior tests because of the fact that we have no final exam right now. Again, this is 2020 first trimester. And we're still dealing with this COVID stuff. So some of the review stuff from the last test, but basics. Okay, so here we go. Exponential decay. We need to know what that is, what it looks like, what causes it. You guys know graph-wise looks like this, right? We know that regardless of what this first number is, it's whatever this number is. So if this number is less than 1, then it's going to decay. I don't care what this stuff is over here. It doesn't matter. So the base below the variable, if it's less than 1, it's going to decay. The only thing that would change that is if we had a negative exponent, and I'm not doing that to you on this test because we didn't have enough time to be able to go through all that stuff. Asymptote, we need to know what those things are. Again, asymptotes are horizontal or vertical lines that a graph gets closer and closer and closer to but never touches. We know that all exponential models have horizontal asymptotes that the graph cannot go. Just to make sure everybody agrees, this is not a graph of that. This is a decay model, but this one's been shifted up 7. So that changes what's going on. You should know what FOIL means. First, outside, inside, last. It's what we use to multiply two binomials together, like 2x plus 3 and x minus 6. You should know different stuff about your graphing calculator. For instance, know your windows. Know how to use your tables. Know how to find intersections. So lots of stuff about your graphing calculator. Make sure you're comfortable with that. So this is our basic one. Know how to store stuff. How to use this button right here to be able to check answers. All of those are really good things. You should know that a quadratic and a parabola mean pretty much the same thing. Okay. You need to know what this is and that its partner is this. And that if I said the natural log of 7, that you know the implied base down here is in E. And if I had a log of 7, that its implied base down here is a 10. Okay, so a log with no base written is implied to be 10. A natural log with no base written is always going to be E. Cool. We know that an E represents continuous change. Continuous. So if we ever see that word in our stuff, we know that we had in this class really only one equation, and that was A equals PE to the RT. We typically would do a few more things with that, but that's where we are. Know that exponentials and logs are inverses of each other, and that log graphs can look like this with a vertical asymptote. And that would be, again, the inverse of an exponential that has a horizontal asymptote. And those are, of course, reflections of each other over the y equals x line, y equals x line. Okay? So again, that's some more vocab stuff. What else do I have here? Know typically in these things what your x variable represents in exponential problems and what your y variable represents in exponential problems. It should be pretty basic based on your windows. Again, I said this before, know your windows. Know that we can solve any of these by guess and check or graphing or logs, and you should be good at all three of those things. And you should know what this means, as I've pointed it out, I don't know, numerous times in this class. Is that good? Anybody out here right now have any questions about any of the vocabulary type stuff that I went through? What do you got? DIMS, right over there on that poster, stands for does it make sense? Right? The thing that we need to ask ourselves every single time that we get an answer out of this calculator. Good? Okay, so we also need to be able to, besides do a bunch of vocabulary, we need to be able to process some of these things. So the first thing I would say is, how about something like this? What's the log of 1/49 base 7 equal to? So if I had a problem like this. Now this is all something that you can do in your brain, right? We don't need to have a calculator for this one. What we want to be able to do is go, hey, I'm going to convert this log equation into an exponential equation. So this would be 7 to what power equals 1/49? And you would go, well, I know 7 squared equals 49, right? How do I get the 49 downstairs? Negative exponent, right? So we know that x must equal -2. -2. Is that good? Everybody feeling okay about that? Now, if you didn't remember that, if you couldn't process that out, since I can't do a non-calc and a calc test this time, it's just a calculator one, so you get your calculator the entire time. Can you do this just in your calculator? Absolutely. The question is, do you know how to do it? Well, for some of you, just a reminder again, clear it out. If I hit the math key and the up arrow a couple times, number A says log base, and I can literally type in my base and the number and answer that question, just like that. Okay, so this would be a base of 7, and this would be 1/49, and I hit enter, and you can see it gives me -2. And you're like, yeah, well, what if I don't have a new calculator that does this stuff? Good deal. Then I could use the change of base formula, and the change of base formula says that I can do the log of 1/49, close parentheses, divided by the log of the base, so log of number divided by log of base, and surprise, surprise, I get -2 there also. So I can use either one of those things to be able to work it out. Which is the fastest way? I think it's just knowing it in your head, knowing the conversion. But if you have extra time, double check your stuff, because again, I've said it over and over again, I can only grade what you guys put. So that's one of the things. You also have to be able to do this. What if I said the log of, let's go 16 base x equals 4. So I changed where the variable was. Before it was over here. We didn't know what that was. Now it's here. Well, the same thing goes into play. We go x to the 4th equals 16, right? base to the power equals that number. It's the conversion into it. And then you guys know that here I actually get two solutions, right? X equals 2 and negative 2. Because 2 times 2 times 2 times 2 equals 16, or negative 2 times negative 2 times negative 2 times negative 2 equals 16. However, we know that this one right here, what? It's extraneous, right? It doesn't work in my original problem because I can't have a base that's negative. Capiche? So I put the variable here, I put the variable here. The only other place is putting the variable here. So know that those are going to be those types of problems. Okay. We did the big one just a few minutes ago, but know that you need to be able to know how to do something like this too. Let's go 1800 equals 3e to the 2x minus 5 plus 17. 3e to the 2x minus 5 plus 17. And it says use logs to solve for x. Okay? So that means that I need you to be able to show me all of these steps. So I'm just going to go ahead and do this one right now for you, making sure that everybody's on the same page. We're going to talk about the tree and the owl again. So the base of the tree is just the e. It does not include the 3. So I'm going to go ahead and isolate that just like that. That's what I have to get alone on this side of the equation. So I got to move my 17. I got to move my 3. My 17 has to go first. So then I'll get 1,783 equals 3e to the 2x minus 5. Divide by 3, divide by 3. Pull out my handy dandy calculator. 1783 divided by 3. 594 and a third. 594.3 repeating equals e to the 2x minus 5. Is this a special kind of tree? Special kind of trees need special kind of loggers, right? What kind of log are we going to use?
Natural log.
A natural log, that ln. So I do it to both sides. ln 594.3 repeating equals 2x minus 5. Now technically, I did the natural log of this, and then I brought my entire thing down, right? But I can only do it once I write that. And we know that the natural log of e cancels each other out, yes? That equals 1. So we can just do that. They undo each other. Yeah? Okay. So now I have natural log of 594.3 repeating equals 2x minus 5. I add 5, I add 5, I divide by 2, I divide by 2. I'll put this on my calculator right now so you guys can see it. So natural log of that answer, enter, plus 5, enter, divided by 2, enter, 5.6937. X equals 5.6937. Ish. Give me a lot of those, right? A lot of those decimal places. And yay, I'm done, right? I just move on to the next question. Is that right, Evan? No, what should I do?
Store it in X instead.
Store it in X. Store it in X. Enter. There we go. And then retype it. 3e to the 2x minus 5. Remember, on old calculators, put that in parentheses. And then plus 17. Hoping for a little 1800 right now. And I got 1800, and I'm feeling pretty darn good about that problem. Everybody okay with this? So now that's one example using natural logs, and we did the other one using the other stuff. Okay? Next, know your log laws. Know your log laws. There are 4 of them. All 4 of them. I'm going to ask you about properties of them, so I'll remind you again. Say the log of 24 is equal to the log of 4 plus the log of 6, because it's the product of these two things that equal that number right there. That's log law number 1. Log law number 2 would say something like this, like the log of 500 is equal to the log of 1000 minus log of 2, because subtraction becomes division or a quotient when we're doing those. Log law number 3 says this, that the log of w raised to the b power equals b log w. And that one has a nickname. What's its nickname?
That's one that's going to be that log.
The log-ride law. This is the one that tells us, right? We get to convert from an exponential into a linear. That was the Michigan Adventure, Cedar Point, whatever you want to call it, log-ride law. Number 4 says this, log of 18 base of 3 equals log 18 over log 3. So be comfortable with all of those properties, all of those things. Is that good? Next. All of the rest of them are, if you want to think about them this way, story problems / I'm going to call them, more importantly, applications. So being able to apply exponential things. Okay, so let's start with this one. Let's go, Mary invests $14,000 at 7.25% interest, compounded weekly for 12 years. Question. First thing I'm going to ask is, what? What was the first thing I ask every time on your quiz? What's the equation? What's the model? How do I represent this situation? Number 2, 12 years equals how much money? And then number 3, the extension. Let's go, when will that investment hit $100,000? How many years? So you guys tell me, give me a quick scale, 1 to 5 in this class. What is your ability to be able to answer all 3 of those questions within, say, like 5 to 6 minutes? 4s, 5s, 4s. That's pretty good. Okay, give it a shot for those people who are out there watching the video. You can pause it right now, give it a shot there, or just chill with us as we're waiting for some people to try it. I'll do a quick walk around. Let me know if you guys have any questions while they're trying to, you guys are trying to, again, you've got to have the right formula first, right? It's just like that, all my keys on my keychain up there, all my keys work, but not if you don't use it in the right place. Remember, there are 3 different banking formulas. There's an annual, there's a compounded continuously, and there's a compounded formula. You need the compounded formula. Okay, just to make sure that everybody's on the right page, because if you're at home right now using the wrong formula, it's just going to get frustrating for you. A equals P times 1 plus R over N to the NT power. This is your compound interest formula, which means you got to use this. What I would be looking for is actually plugging that stuff in. So A is the variable we're solving for. 14,000 is our principal, or how much money we put into the bank. 1 plus interest rate. You have to move the decimal 2 places. 7.25% becomes 0.0725. Since it's weekly, that happens 52 times per year. And then 52t. This is the general equation then. And then on number 2, we're going to actually plug 12 into that t to be able to solve for that. So if we don't have that formula, it doesn't matter anything for the rest of the stuff that we do. You got to have the right one. And it's this one because it says compounded weekly. Good deal. At this point here, I'm going to go ahead and do number 2 since we all have that same equation. I'm just simply going to type this in to my calculator and plug 12 in for the number of years. So 14,000 parentheses 1 plus 0.0725 divided by 52 close parentheses raised to the parentheses 52 times 12 close parentheses. Double checking because again, as soon as I hit enter, I'm going to probably write down that number. So if I type in the wrong stuff, I'm going to get the wrong answer. So 33,396.5, 33,396.5. One if I want to put that extra penny rounding that up. Good. Next, when will it hit 100,000? Well, it took 12 years to go from 14,000 to 33,000. So I'm thinking my years are probably going to be up there a little bit. So I have 2 options right now. I literally could use my algebra and solve it with logarithms. But I think this piece of technology here is really nice. It just depends on how good you are with your windows. So I'm going to go ahead and do it with graphing because I said any of the story problems you can use with graphs. So go to y equals clear and clear. So I got 14,000 parentheses 1 plus 0.0725 divided by 52 close parentheses raised to the parentheses 52x close parentheses. Here I have to use x because I don't know how many years it is. That's what we're trying to find out. Okay, so please don't retype it in with 12. You're going to get parallel lines running across your screen. It's not going to make any sense. Use x. Now in y2, I want to know when we're going to hit 100,000. So here's where I have to be smart enough and understand the question enough to get a window that makes sense. So one more time. It took me 12 years to get this far, and I'm trying to get it all the way to 100,000. I might just go ahead and put it at 40 years. I think in my brain it's going to happen before 40 years. In fact, I think it might even happen before 30 years. It's going to be close to that. But going to 40 is not bad. What's bad is you guys doing this and putting 150,000 in here thinking that that's the money. No, x is always the what? Time. X is the time. How many times we're repeating this? So please don't put that in there. So 40. Down here, 150,000, that's a great place to put that. Graph. Oh, I don't know. There's just some sort of satisfaction when you get the right window and you see it showing up on your screen. You're like, yes, I nailed that. Second trace, number 5, enter, enter, enter. 27.14 years. 27.14 years. Good. Now, I don't remember if I put tenths or hundredths, but I put something on there. Please don't just say it's 27 years. You can guess that way. I want to know that you use logs or graphs to be able to do that. Ella, what you got? What did I put into what? I put in 100,000. Did you say Y2? Because we wanted to know how many years until her money was worth $100,000. Is that good? Okay, so that's one of those types of problems. So if I extended this again and I said, hey, what if I asked the same questions, but I compounded it continuously? Which means instead of interest at the end of every week, we get the interest at the end of every, like, millisecond. That fast, right? Which means, here's my things again. 1, 2, 3, yes? 1, 2, 3. A equals 14,000, right? E to the 0.0725 t. Because the compounded continuously formula is the PERT formula. A equals PE to the RT. Yeah? That should be in our notes. That should be golden. So that's my equation, and then I plug in 12 for this. So, big question, should the monetary difference be that much between paying interest every week and paying interest every millisecond? No. Answer is no. It should not be that much different. It should be more though, right? It better be more. If it's not more, we're like, oh, something's not right. So I go here, 14,000 E 0.0725 times 12 years. I get $33,416.75. $33,416.75. Okay? So literally like 20 bucks more. Right? Isn't that 20 bucks more? So we got $20 more, $20.21 more, or 24 cents more than we would have if we got it weekly. Now, granted, this is more than we would have if it would have been annually, which would have been our first situation. And then the last one, to get to 100,000, I simply go here. 100,000 goes in this one. 14,000 goes here. Yes. E 0.0725x. Put it in parentheses on your old calculators. Yes, put it in parentheses on your old calculators. Dan Clark, should I change my window, or is my window probably still good because it's the same stuff?
I think it's the same.
I'm going to keep it the same and see what happens. That looks pretty good to me. Second trace, number 5, enter, 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 27.118, so 27.12 years. So literally we're talking about the difference of, I don't know, maybe 4 or 5 days in interest to get there. Yeah? So everybody, we feel good about this? Okay. Next, what about something like this? I think this is probably my last one for the video for you guys at home. Let's say that I had a rodent population. Unfortunately, they're bad. 1,864 of these rats. And we're trying to eliminate them. We're trying to get rid of them. And we put traps down. And we feel like the traps are going to knock off about 12% a month. 12% a month. So my question is, how many months until we are under 500 rats? How many months until we are under 500 rats? So that would be an exponential situation, because we know the percentage changes per month. Now, some of you are going to freak out right now because you saw the word month and you're like, oh, I got to use that compound interest formula. No. That just simply means that this is our time period. It could be, right, that time period, like our bouncing ball, was every bounce. It's just how many times we have to repeat that multiplication. It could be that things change by the second, and that's our unit, okay? So this month doesn't mean that. This means that this happens one time in a month. So I write my annual, my single amount change, 1,864, right? And this is critical. What do I put in here? I put in either 0.88, right, 88%, or I put in 1 minus 0.12, because those two numbers are the same. Yes? So I had 100% of the rats. I'm losing 12%, and I'm losing 12% per month, whatever that time period is. Just know that this isn't years anymore, right? That this is months. But I'm going to figure out what that is. And I want to know when it equals. I want to know, when does A equal 500? Don't put 500 in for M. That doesn't make no sense. That'd be 500 months from now. How many rats are there? Probably not any 500 months from now. We want to know when A is 500. So you have options. Show me hands. I'm just curious in this class right now. How many of you would use a logarithm right now to solve this? Nobody. How many of you would use a graph to solve this? Okay. How many of you are already done? One. Okay, you guys go. I'm going to use logs. You guys use your graph, and we'll see who wins. I'll even go slow. Type with my just one finger. Oh, I'm done. Hello. Absolutely. We are rock starring with our calculators right now, doing a little review. She's going to take pictures for the math department, so look mathy and calculatory and paying attention. Are you guys good with that? 10.29? Is that what you got when you did it, Mr. Boyle, on your graph? Yeah. I don't know. How long did that take me using logs? Like 23 seconds, typing slow. So no, that's okay. But wait, I'm not done, am I? 10.29 months, right? So less than a year, What should I do with that? I should store it in my X and then retype this equation. 1864 parentheses 0.88 close parentheses, raised to the x. Dun 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 dun. Bam! 500 rats. Ibuki, you feeling good about that? Yeah? Calculator getting better or no? No? Okay. But can you use logs? Yeah? A little bit? Oh, you're up. Okay, so, yeah? We're feeling okay? So at this point right here, all the rest of the problems are types of applications. You just got to know which formula to use, which time when you're plugging the stuff in. Is that good? Nick's like, dang, that was a close-up right there. It's like, okay. So, yes? No? Maybe so? Anything else that I can do for you? All of you at home, practice these ones. Write down those things again. Try some different numbers. Plug them in. See what is happening. Do your homework, too.